Yo. Got the chat open if there is anyone here. We are continuing where we left off yesterday on Pytorch Lightning, but today we have a goal to do it with Whisper. So the goal for today is see if we can fine-tune Whisper using Huggingface, and then if we can use Pytorch Lightning for it. So what's up, guys? So for the people that weren't here yesterday, what we did is we had this bare bones implementation of variational autoencoder that I did. I made a video on this, so this is just the exact same code, but this is just bare bones PyTorch, and we took that with the model and the train, right? And in normal you have sort of with all of the training setup and stuff, but then we converted it to PyTorch Lightning so that in the training function we instead used PyTorch Lightning Trainer, which has benefits like more flexibility and stuff. But then we also changed the model so that it's a Lightning module, and that way we can I don't know, like it's that way we write the just the setup or the structure that PyTorch Lightning wants, with training step, validation step, test step, and so on. And then, oh, what happened? There we go. And then we did a data set with Lightning data module, where you do a setup, we loaded the MNIST data set, and then you return the train loader. So that's what we did yesterday. Today we're going to be, I don't know if we're going to succeed. It's going to be quite ambitious. I'm running on a Mac laptop, and then I SSH to a Linux machine that has two 3090s. So that's my setup. All right, so let's make a plan for this. I don't have one. I have no idea what I'm doing. Let's see. So I know that there's a Finetuning Whisper Huggingface, and I've checked at this a little bit, and I was thinking we can go through this stuff. And try to re-implement it, but then try to combine it with Lightning. I might want to, before we get too deep in this, there was something I wanted to do yesterday actually with PyTorch Lightning. I remember now. I wanted to learn how to do the, let's see. Yeah, we yeah, right. I remember now, actually. Okay. So our goal for today is still to do the whisper thing with lightning, but I want to know or learn how to do the multi-GPU setup. So we want to know in this train thing how when we do here, we can do strategy, and we can do DDP for this data distributed parallel. We can do what else can we do? We can do deep speed. We can do, I don't know, there was some other stuff as well. Horovod. I don't know. There was some strategy. There was some other one. We can do like this. Strategy, use fair scale. All right, maybe it was this, but then you could do DDP. You could do sharded. And I don't know what any of those are, so that's what I would like to figure out. I don't know about this music though. I'll just put it on. I don't know. All right, I'll pause it. Well, okay, maybe it's pretty nice then. I don't know. Let me know what you think of the music. All right, we were watching a video, I think, this one. Let's just watch that one. And let's pause this music. So this is why I initially wanted to learn about PyTorch Lightning, so that we can do like this thing, for example. This zero paper. Can you do zero optimization? There we go. Is it? I think it's this one. But there's been updates on this, so. But yeah, this is I think one of the like state of the art when it comes to sort of multi GPU training. Zero redundancy optimizer 0 to optimize memory, vastly improve training speed while increasing the model size that can be efficiently trained. So it does cool stuff. Like you can do just basically copy the model to both of the GPUs and then run data on both. If you can, that's when you can do your model on a single GPU. But obviously, if you're doing something that has a trillion parameter models and stuff, then you can't do that all on a single GPU. So you'd have to distribute the model weights as well. So that's what they try to do here. And I have like I'm just learning about this, so I have no idea exactly how they do it. But you know, as a guess, I guess that they take the parameters of the model and you just split it. But then they have to do that in some smart way because there might be delays and stuff that slows down training a lot. Yeah, I don't know. The goal is not to learn about this today, but just to know how to use it, basically, using Lightning. But yeah, I was hoping to get like an overview, and I think this one they had was pretty good. So let's take a look at that. Maybe we can learn some about how they do the training and stuff.
Hi everyone, I'm William Falcon. I'm the creator of PyTorch Lightning and the co-founder of Grid AI. And along with Sean Nairn today, who is one of our research engineers at PyTorch Lightning and is doing incredible work at helping Lightning scale up your models. So today we're gonna talk to you about sharded and how to apply it to getting models to train at scale. So if you've tried to train at scale, across many GPUs or many nodes, you know that there are a lot of challenges. So we're going to cover three things today. We're going to teach you how to do training at scale with PyTorch Lightning. Then we're going to talk about distributed training. And then we're going to talk about sharded training. So how do we train large models longer and faster? You have to overcome three bottlenecks. The first one is speed. The second one is memory. And the third one is the actual implementation. So speed is very critical when you're going through the model iteration process. So you have an idea, you have some data, and you want to use machine learning or deep learning to get something out of it. The faster you can try ideas, the faster you're going to find results. So let's think about solving a problem. And if you think about this kind of random walk process where you're going to try things and eventually you're going to find something that works, well, it's going to be a sequential process if your training is too slow. That means you're going to try one idea, tweak it a bit, try another idea, tweak it a bit, try another. And that process is going to continue until you're hopefully at a place that you can productionize the model or publish a paper. Higher memory capacity means you can have more parameters and more data on memory. So your batch size can increase and your model.
When I first saw it like this, it surprised me. I didn't realize that the optimizer states was taking this like the chunk of the VRAM when training. I had this idea that the parameters of the model was what was taking the most, but yeah, my intuition was not correct there. I guess it's a little bit. I don't know exactly what's in how that could be taking so much VRAM, but yeah.
Can increase as well. And we know that model size is very correlated today with really good performance. And unfortunately today, you have a lot of things that take up memory. So you have your actual model weights, you have the optimizers, which can store copies of the weights as well. You have the activations, you have temporary buffers, parameters. It really adds up. And you end up using a lot of your memory for overhead instead of actually the data or the weights themselves. And finally, this is really hard to pull off. You need a lot of esoteric knowledge to get every single detail right about distributed training. And that's a lot of what our team focuses on. We spend a lot of time doing this so you don't have to do it. And the problem with doing this at scale is that if you miss one single thing, your model will be a little bit slow, things may not converge. So you spend months just getting all the details right before actually getting something to work. So that's really where PyTorch Lightning comes in. Lightning makes coding neural networks very simple. So here's an autoencoder, and you have basically four methods you care about. The init is where you instantiate your model, or you can pass it in if you want as well. The forward is anything that you want to use for inference. The training step is the core logic, right? So it's everything that's going to go inside your training loop. And then the optimizers method basically lets you define what optimizers and learning rate schedulers are going to be tied to this model. What's really cool is that everything's self-contained, which means it can run on arbitrary hardware. So you can run on 1 GPU, 10 GPUs, 200 GPUs, CPUs without changing a single line of your code. Lightning is really designed around four principles. The first one is self-contained models and data. So to show you the value of having self-contained models and data, take a look at this example. I have 3 models and 2 different data sets. Because everything's modularized and self-contained, I can mix and match them as much as I want. A good test to see whether your model is self-contained is whether you can drop it into the Lightning trainer and it'll just work. The second one is modular code standards. So let's take a look at your deep learning code. Imagine every one of these lines is a line of code. So we're going to factor out your code into 3 parts. The first part is going to decouple the research, and that's going to live in the Lightning module. This is where you want to spend 99% of your time. The next part is to decouple the data, and this is going to live in the data module. And the data module encompasses the data loaders, the transforms, and everything you need to make that data set self-contained as well. And then everything else that is left is going to be automated by the trainer. So this is the boilerplate that most people get wrong. and there's a lot of surface area for errors as well. And the final principle is full flexibility. So I had been using many machine learning frameworks for a few years before I started working on Pytorch specifically. And something that I really cared about, as I was doing research and also putting things into production, was the ability to customize code. So what I didn't want to end up doing was getting onto a framework, it's easy to get on, and then 6 months later you find out that you're blocked because something is no longer accessible. So I wanted to make sure that at the DNA of Lightning, it was this ability to be really, really highly flexible. So how does Lightning do that? It's by giving you this access to hooks. So anytime you want to access any part of the training loop, you're able to just kind of plug into a hook and do what you need to do there. So once you convert your code to Lightning, you get a lot of features out of the box. So some of the most basic features are different accelerators. So you can turn on 1 GPU, 8 GPUs, 256 GPUs. You get automatic organization for your artifacts. You get checkpoints, you get logs, you get everything you need to be able to do productive research. You get profiling, many different profilers.
So all of that stuff is what we did yesterday, I guess. And it was really easy to set up, actually. The callbacks, there's a lot of callbacks, and we haven't done a deep dive on that, but on the surface level, they seem easy to use. And then just TensorBoard logger, where you just kind of put it here. So we did you can log the training loss, and sometimes you log the images, in this case for generation of MNIST digits using VAE, and it was nice, pretty simple and pretty easy. The only thing I wanted to add was the scheduler. So have a reduced learn rate on plateau, and we had to do that here. I didn't like doing it here because I want to have everything in the train. So now we set up the learning rate here, batch size, number of workers, and so on. And it would be nice to just scheduler, etc. And I guess you can send that into the model here, the scheduler and stuff. But I don't know. I haven't read that much code, so I don't know how people what the standard way of doing it is. I'm kind of figuring it out. So that's I remember that something I wanted to do yesterday, and then the strategy used for multi-GPU training. If we run this now on a single, we can specify the devices. So let's say we just use device 0, and we use we can use this is fine, and logger and GPU. And if we just run this now and we do let's see. All right, so it's running, and then we do NVIDIA SMI. We see that the model is just taking 400 megabytes, which, that's tiny, right? This is just a really simple model, but it's taking 400 megabyte. But if we use devices both, and we rerun that, oh, it's taking forever. I guess that's the number of workers, maybe. Okay, now, all right, there we go. So if we now do that, watch NVIDIA SMI, we see that it's taking 400 megabytes on both. It's actually taking a little bit more on both, but that's fine. It's copying the model on both, and it's running on both, and that will be a lot faster, right? Now we're utilizing both GPUs. which is nice. But what if we had a model that's too large, that we can't fit it in a single GPU memory? Then we want to know how to split the model on sort of the model parameters on both of the GPUs. And that's what Lightning can do for us, but I don't know how to do it yet. So there is, like, if we ask Copilot, I guess we can do like, yeah, that's another thing as well. We can do precision 16 or BF 16 maybe. Not sure which one to use as default. Like the precision is, from my understanding, better with B float 16. But I don't know. It doesn't seem to be a big difference because I've seen people use both float 16 and B float 16. I don't know. So right now I'm just using, let's just do 16 for now. And then if we do the strategy and we ask Copilot to do, let's do like this. Since model is too large for single GPU need to split parameters to multiple using 0 stage 2. Okay, we have no idea. And then let's see, strategy. God damn it, it didn't get it. Make sure we can use deep speed for 0 stage 2. Plugins. Oh, and then we need to have a deep speed config. Okay. Okay. So there's going to be some with the plugins and probably some with the deep speed config. Let's see if that's actually there. Or if it's just making stuff up. If Copilot is just making stuff up. So wait, what did we call it? Plugins. Okay, plugins actually do exist. Plugins allow modification of core behavior like DDP and AMP and enable custom Lightning plugins. Well, I mean, I guess that could be it. And then we had one called deep speed config. That doesn't seem to exist, so. All right.
You get checkpoints, you get logs, you get everything you need to be able to do productive research. About sharded soon, distributed data parallel, many ways of doing distributed training. You can across the world, PhDs, professors, research scientists in industry, academia, who are all doing their work and putting all of their energy, who are coding things not just for themselves, but for the community. So Lightning is a community-driven project where it's basically the world's research lab. So anyone who wants to do anything can contribute it to Lightning for everyone else to benefit from it. So now I'm going to pass it over to my colleague Sean, who's going to go into details about how to do sharded and scale up your models.
Thanks, Will. We'll be delving deeper into some of the technical details, particularly around training, scaling, and being able to reach those really large parameter sizes. We want to strive for implementations that work not only on those 1,000 GPU clusters, but also to limited compute. At Pytorch Lightning, we work closely with teams to provide the fastest API to enable these optimizations, which have allowed sharded training to be adopted by many researchers. But before we jump into sharded training, I want to ensure we understand what's happening at simpler paradigms. Now, data parallel is a very common procedure that's used by many users. I have one model, and I would like to scale to multiple GPUs. How could I do this? Very intuitively, it makes sense to just scale the data. if I replicate my model across my GPUs and provide a different batch of data for each one of these GPUs, I can scale my training from a data level. And most users are familiar with this. In PyTorch, this is data parallel, or DDP, distributed data parallel, and has become a staple of training, and the elegancy of it makes it very widely adopted. We're going to move a layer deeper, and I'm going to go through a training iteration using data parallel so that we understand what's happening under the hood to give us a better idea of what's happening within sharded training. Now, there's many moving parts when we have a multi-GPU cluster and we would like to train, even for data parallel. So let's start with 2 machines with 4 GPUs in. Now, we have to start with choosing what our rank assignments are, making sure that each GPU and every machine knows where they sit within the world. Now, something that's very overlooked is making sure that we start with the right random seed for each process, and this is something that's handled by Lightning. This is important to make sure that we have the right ranks for data loading, for data splits, and any form of model initialization. We start with initializing our model across all processes. This means the same model exists on every GPU, and this is important. Recall how for data parallel, all GPUs need to have the same model replicated. Now, during our forward pass, each GPU gets a different batch of data or inputs. This is the data parallel piece, making sure that we scale our data across all the different GPUs. And this is what allows us to scale what is called the effective batch size. Through our training process, we pass these inputs through our model, get some form of output, and calculate some form of loss. Now notice how the loss is different for each one of these GPUs. And this makes sense because the data that was received for every single GPU is different. Now, during the backwards pass, we will calculate gradients with respect to the local loss for each GPU. So now we can probably see a very crucial point in the communication. If we were to just do an optimizer step for every single GPU now, they will all end up with different weights. So at this point, we have to do some form of synchronization. Now, depending on how it's implemented, this gradient synchronization can happen in a ring or any form of communication pattern, but at the end of it, we're trying to get the same gradients on every single GPU. And this goes through a process of either the GPUs talking together or in some form of cycle. And we end up with the same gradients across every single GPU. Now, a slight mistake here is that we use L1, but just imagine now we have the gradients, the same average gradients on every single GPU. Now, if they were to do the optimizer step, this means they will all end up with the same model. And this sets up well for the next iteration as we continue the forward and the backward process. The benefits of data parallel shouldn't be taken lightly. Here we have a graph from the infamous DeepSpeech 2 paper by Baidu, which really pushed the boundaries of what's possible.
So this is, I mean, we got this working, and this is nice. It definitely was faster with using both GPUs, but I still want to learn how to do it with splitting the parameters of the model because you know, some of the large language models, you know, they're just impossible to run on a single one.
Speech recognition. And here they train up to a maximum of 128 GPUs, and this allowed them to reach state-of-the-art results in speech-to-text, paving the way for end-to-end training on very large compute. But what about scaling model size? Data parallelism is great to scale training if my model fits on one GPU. But what happens if my model doesn't fit on one GPU? What if I want to see how big of a model I can train, but I don't really have the memory to really scale this? We start to move towards something called model parallel, a potential answer for scaling our model sizes, reducing our memory consumption, and allowing us to reach further into state-of-the-art results. And it goes without saying the benefits of scale. Recently, we've seen massive jumps in parameter sizes, showing new behavior such.
Have you guys seen the posts on Twitter and LinkedIn all saying that GPT-4 is going to be 100 trillion parameter model? You know, I'm skeptical that it's going to be that large, to be honest. But I wonder how large it's actually going to be.
Zero-shot, cross-lingual, and NLP, and we're starting to see similar trends across modalities. Scale will continue to prove crucial, and ensuring we optimize for memory and performance is important. On the flip side, for researchers who do not have access to these thousands of GPUs, fine-tuning these models or even reaching larger model sizes on limited compute is also important to forward research in the community. As we scale these models, it's important that we don't lose sight of the accessibility to research, where compute is limited. Now, these would not be possible, these results you see right now, would not be possible without model parallel or some form of optimized distributed training. And to give us a sense of what makes these results possible, we're going to break down the solutions to scaling that have been used and figure out where sharded sits within this world and how it could be the solution for training these really large models. We're going to break down these solutions into two sections. Now, both try to target the same problems of trying to reduce memory consumption and scale our model size, but they take a slightly different approach. And we'll step through both, but right now we're going to talk about what true model parallel is. True model parallel is simply splitting your model across whatever available compute you have, normally GPUs. Intuitively, this makes sense and opens up the possibility for larger models. This diagram was taken from a recent paper around mixture of experts, scaling to a ridiculous trillion parameters. And at this scale, you really have to consider splitting your model. Just imagine the amount of weights that need to be stored and iterated through the training process. Now let's delve a little bit deeper into what these ways of splitting are. One way that's very intuitive is to just split the layer vertically. Now, in very particular cases, this can be useful, primarily around embedding layers. So imagine taking a really, really large embedding layer and cutting it into two and putting one on each GPU. Another one could be some form of very complicated classification task, but at the end of the day, this requires a very specific implementation per layer, but it works reasonably well and stays somewhat elegant. Another way is to split the layers horizontally. So imagine if I have a stack of layers. I can just do what's called a pipeline. So each one of these layers would end up on each GPU. But this gets a little bit tricky because imagine if I have an attention block that's taking much longer than one of my linear layers, I have to start thinking about how would I balance this correctly. And that can be a very tricky task. A lot of manual tuning is required, and even the implementations can be very, very tricky and dense in terms of boilerplate and code. Now, self-balancing architectures is something that's very highly requested in Lightning, and we are exploring this, but it's an extremely challenging problem. Overall, we're starting to get a sense of why true model parallel is not simple. Now, as you can see from this diagram, there are many ways to split the model, and in many implementations, this isn't automatic. Determining what layers go onto which GPU is an art itself currently. Now, work has been done to try and automate this in the future, and we're looking forward to seeing what is possible in this field. More important, and especially towards accessibility, these implementations are complicated and require a lot of user intervention and tuning. The benefits are incredible and cutting edge, don't get me wrong. However, for a rapid research cycle, this really hinders the overall research project and the application and scale we can achieve on various modalities in research projects, which at PyTorch Lightning is super crucial to us to provide and support. Now, motivated by the difficulties of true model parallel, let's try and find something that's more general, more applicable to a larger set of research projects and modalities. And we'll talk about something I've coined as optimized distributed training. Now, we're starting to realize there's a lot of pain points and difficulty of model parallel. We now know the lack of applicability to a lot of models and research projects, and the complicated code that comes with it to try and implement, and a lot of the user intervention that's required. The DSP team at Microsoft realized that there was a lot of redundancy with how data parallel works when we scale up.
So this is one of the, when we were just experimenting yesterday, we used DeepSpeed, we downloaded DeepSpeed and Fairscale, and I have no idea which one we should use, like Fairscale versus DeepSpeed, which one is the best. I guess maybe both work.
And this diagram you see was taken from a great paper that they released called Zero, or Zero Redundancy Training. They asked the question, when we scale our model, can we leverage distributed communication to reduce the memory on each GPU? I.e., can we do something a little bit smarter than just replicating our model across all GPUs?
I mean, just based on the stars, we have 2K for fair scale, 8.6 for deep speed. So maybe deep speed is the way to go.
The team also had the similar idea, motivated by what Microsoft released in terms of Zero, and have been addressing the same question, just a little bit more closer to Pytorch and coining the name sharded training. They all have the same idea. Can we just reduce the duplication required, and then can we save memory ultimately? And then can we use this memory to either train on limited compute or even scale our model size further? Before we talk about how to solve the redundancy, let's talk about what redundancy there is in terms of memory. Imagine you have a GPU and you would like to train a model. Some of you may already notice that the model itself only takes up a very small portion of the memory, looking at NVIDIA SMI or NVProc. There are many other factors that you have to consider when training a model and take up the rest of your VRAM. Let's take the optimizer state. A commonly used optimizer, Adam, requires storing multiple values for each weight, taking up much more VRAM than the initial model. On top of that, if anyone's using mixed precision, it means we commonly have to store a floating point 32 copy of the weights and parameters. Gradients and activations are also stored. Activations are stored for the backwards pass. Finally, any form of temporary buffers that can store intermediate states also sit on top of your memory usage. And now we see a complete view of why our model, or our large model, cannot train on one GPU, as there's all these other things that need to be allocated. So instead of duplicating everything, or the model, onto every single GPU, a solution to this problem may be, can we partition the model onto every single GPU? So each GPU only has to care about a portion of the model. And why not shard everything? Let's shard optimizer states, gradients, and obviously the parameters. Now as a solution, this seems very elegant, and it makes sense that every GPU only has to care about a portion of the model parameters. And naturally, we can start to see that if we do this, we reduce the overhead required for each GPU, meaning we can start to scale our model sizes. Now we can see how we can fit much larger models onto our GPU if each GPU only has to care about a portion of the model itself. However, we can start to think about the additional complexity of the communication. If everything exists on different GPUs, this probably means that the GPUs need to communicate much more. How do we ensure that every GPU remains in sync? We cannot lose too much of the efficiency of data parallel, or will make it far too inefficient to train. To maintain the same performance, we have to consider communication, and we do this in two ways. We can replace the communications with something smarter, knowing that our model is now sharded across different machines. You may recall that before we used an all-reduced step for synchronizing.
All right, so what does, okay, wait, so we have multiple GPUs, we have multiple data sources, we are running, okay, so this data is running on, I'm a little bit confused here, this is not model parallelism, is it?
So required for each that one GPU. As maybe can we partition the model onto every single GPU? So each GPU only has to care about a portion of the model. Not shard everything. Let's shard optimizer states, gradients, and obviously the parameters.
Okay, so we just sharded means that we split all the parameters of a specific block into the different GPUs. But why is, so this here is data on different, not sure.
Now, as a solution, this seems
basically, if you run data, this part of the GPU is responsible from the beginning, and then we have, so that we split the, basically, I'm just a little bit confused what sharded is, how sharded training is different than just model parallelism, but maybe
very
he'll get to
elegant.
it.
And it makes sense that every GPU only has to care about a portion of the model parameters. And naturally, we can start to see that if we do this, we reduce the overhead required for each GPU, meaning we can start to scale our model sizes. Now we can see how we can fit much larger models onto our GPU if each GPU only has to care about a portion of the model itself. However, we can start to think about the additional complexity of the communication. If everything exists on different GPUs, this probably means that the GPUs need to communicate much more. So how do we ensure that every GPU remains in sync? We cannot lose too much of the efficiency of data parallel, or we'll make it far too inefficient to train. To maintain the same performance, we have to consider communication. And we do this in two ways. We can replace the communications with something smarter, knowing that our model is now sharded across different machines. You may recall that before we used an all reduce step for synchronizing our gradients across processes when using data parallel. Can we do something smarter once the model has been sharded? Secondly, we need to parallelize as much as possible. This means ensuring we fully leverage the machine and the communication bandwidth as soon as possible. Most importantly, each GPU should still receive its own batch of data, and this can be a bit tricky to understand how this could work, and we're going to detail the steps required for this. So firstly, let's talk about communication. The first thing we can do is try and replace the all reduce with something smarter. And we already know now, if our parameters have been sharded across different GPUs, we might not need to communicate everything to each one of the GPUs, as only one of the GPUs cares about a particular portion of the model. However, we want to parallelize as much as possible, and the solution for sharded training is to replace the all reduce with something called a reduced scatter. Now, for the sake of this demonstration, let's assume in this diagram that every GPU has access to all model parameters. It's just the optimizer state and gradients that have been sharded. Now imagine we're calculating the gradients for P0. So let's imagine in this step, we would like to calculate the gradients for P0. Now all the GPUs do have access to all the parameters, so that you can all calculate the gradients with respect to their local loss. But when it comes to the actual gradients, only GPU 0 cares about the gradients for P0. And we can use what's called a reduce rather than an all reduce to send these gradients over. This is faster than an all reduce and means every other GPU that doesn't have to care about P0's gradients can discard them straight away, which saves a lot of memory. However, after all the gradients have been properly averaged and given to the appropriate GPUs, for the next training iteration, we still need to synchronize the parameters if every GPU has access to every single parameter. So this is what's called an all gather, where we gather all the different parameters from all GPUs and collate them onto every single GPU. This means that once we run the next training iteration, each GPU will have access to all the parameters and have a synchronized state. Now this reduced scatter and all gather that happens is roughly the same amount of communication that would happen normally during data parallel. Let's go into a couple of the technical details when we're using the same concept, except now this diagram holds true. We split the parameters onto every single GPU, and if we'd like, even the activations. This does come with a larger communication overhead, as we have to communicate with each GPU in order to get the weights to calculate our forward passes and our backwards. But this gives us a massive improvement in terms of memory and the scale of model we can achieve. Finally, the last concept I'll be introducing today is CPU offloading. CPU offloading is fairly simple. Instead of keeping states, gradients, and even parameters on your GPU memory, why not pass them to the CPU and prefetch them on demand? Obviously, this comes with the overhead of host device transfer. However, it allows us to reach these monstrous 1 trillion parameter models on 128 GPUs, as reported by Facebook Research with their release of fully sharded training. We've worked closely with the Fairscale team to ensure seamless integration of sharded and...
This is what was that library called? There was one, I don't remember, but I think one big thing is, obviously we don't have access to 100, like it's impossible for a person to sort of train or be able to rent that large GPU clusters, right? That's only available for pretty much OpenAI and, big companies that have access to it. But I think there's some interesting approaches going on and research in being able to sort of do open source training so that basically you can join on a like on a network where we can all utilize our own processing power and combine it in smart ways so that we are able to train really large models. And I guess if you set up a system where if I sort of lend my compute power to another guy's project when I'm not using it, then I sort of can use that back for a project I'm building where I need compute. And I really like the idea of that. But I guess it's in the early phases. But if that becomes possible, then imagine what cool open source machine learning applications you can build that are, truly open source, where you don't have to be behind a big company like OpenAI. Because just imagine, like ChatGPT, right? Imagine when ChatGPT gets to know you and knows you as a person. And just imagine if, the power that they have of that. And you really put a lot of faith in the company and that, it's like that you trust them basically, because they can do a lot of, if they were malicious, then, it could turn out bad. So, just something that sparked my, an idea here where they're talking about this fully sharded training. I don't remember what the library was called though. I'll check it. I can't find it. Maybe this pedals. So here we go. Run 100 billion plus language models at home, BitTorrent style, fine-tuning and inference up to 10 times faster than offloading. This idea I really like. Imagine if we get this working really well and you can join like a swarm, a public swarm, and you can make these actually open source. I mean, that would be awesome. And I guess it's already up and you can already join it. But probably it's in the early phases. It's not perfect, but yeah, anyways, let's go back to the thing.
Fully sharded training.
Yeah, how do you serve a PyTorch model? I'm still learning about that, but right now I'm doing PyTorch serve, and either you set up your own hosting of the model, or you set up sort of AVS hosting, and it depends on, live inference is obviously a lot more expensive to rent, but you could do sort of batch inference during specific sort of times, and that would be a lot cheaper. And you can set up a server on AVS with Torch Serve. I haven't done that much. I did set up on AVS Lambda, sort of a serverless, and it was not the most pleasant experience. So I hope that they've improved it a bit, but I think it is a learning curve, and there's a lot of stuff on AVS, so it's not that clean. I haven't tried Azure and others though. I've only used AVS.
It is important for us to provide a usable, robust solution out of the box and help the research community use these tools to build larger models and reduce memory usage on accelerator flag to DDP.
So we've done that, DDP. How do we do it on?
In this case, all we have to do is add an
plugins. Okay.
additional flag.
All right, let's do plugins. DDP sharded. Let's see if that works. Nope. Found invalid type. Not sure why this is not working. Found invalid type. Maybe it's the checkpoint. Yeah, it's probably changed since then. This is 1 year ago. Yesterday we watched some tutorial videos that they have, which was also 1 year old, and like I think 3 of the 10 videos had an outdated API. So, you know, I said yesterday I'm kind of afraid of making videos on PyTorch Lightning because they're going to be outdated, but that might just be the way it is. Probably it's not that big of a change. Oh, what the hell? I have no idea what I'm doing. What happened? Whoa. Okay. Okay. I don't know what happened there. All right, so it worked with DP. It's still using same amount of VRAM on both though, so I guess this is the same as DDP probably.
To work a bunch, which again follows a similar API. That's the model, not just a single.
All right, so we should be able to do DDP fully sharded.
I've been using grid. I could use the CLI experiment with its intuitive.
I don't think PyTorch Lightning is a replacement for PyTorch. It's just a wrapper. It's just built on top of it to build standardized coding structure of your training and stuff like that. So I don't think the goal is to replace. It can't replace. I mean, it's just a wrapper. You can sort of view it like Keras on top of TensorFlow.
Were collected on an AWS instance with multiple
All right, Lightning sharded benchmarks, peak memory usage. All right, so DDP plus sharded, it uses less VRAM, and this is what we want to see, and the average epoch time.
Fully sharded training coming soon to Lightning, we see even larger jumps in our model sizes. Recall, fully sharded additionally partitions or shards the parameters.
All right, so let's see, PyTorch Lightning sharded training. Hopefully this one is updated then. Colossal sharded training. We tried that, but it didn't work. DDP sharded. Okay, it did work. But this is the strange thing. It's using more VRAM on both. So I don't know how that's possible. Like you shard, but it uses more. I don't know how that makes sense. It uses, so if anybody can explain this, it would be nice. So look, if we do on a single GPU, it uses 400 megabytes. If we use DDP, it uses 400 megabytes on both. If we do DDP sharded, it uses 2 gigabytes almost on both. That doesn't make any sense to me. What is it? Root shard detect the trainable parameters change. All right, I guess maybe that's true. I mean, we're using a really tiny model, so maybe if we would have made it larger, then maybe it would have. Okay, deep speed zero stage one. Shard optimizer states stage 2. Okay, and then if we just try this, then just deep speed stage 1, what happens? Okay, setting train GPU is deprecated. Okay, we'll set devices instead. What else? Try to infer the batch size for internal deep speed logging. Strategy, deep speed strategy. Okay, so we'll try that. Okay. All right, so maybe that's how you're supposed to do it. I don't know. Deep speed stage 1. What error did we get anyways? Ninja, no work to do. Oh. Okay, wow. Okay. It's just making shit up. Stage. Just stage, okay. It literally made up all the keyword argument. I don't know what that is. Current loss scale already at minimum. Cannot decrease scale anymore. I'm not sure. Maybe we can try on the other project we did. Hmm.
Each one of our devices, which brings our memory.
All right, I don't know. I'm not 100% sure why that's not working. I don't see anyone having the same error, so maybe there's something. Oh. Logging batch size per GPU. Trying to look for if they have an example where you can run it, because it would be nice to start with something that works, and then you can maybe see what's different from our setup to theirs. But I don't know. Because like it's running, but it's giving just loss scale already at minimum, so that maybe it's like our model and stuff where it's just not suitable for this deep speed strategy maybe. Oh, it's set to default, true. Stage 2. All right, it's fine. We'll figure it out. Maybe it would have been cool to get this to work, but I can't figure out that error message. FP16, maybe it has to do with that then, I'm not sure. Okay. I mean, it's using more VRAM than there's definitely something that I'm not understanding, because one GPU is using 400 megabyte, and then two devices with sharded, it's using 4 gigabytes each. And this is a tiny model, so I don't know, but we'll, when we actually need this, we have an idea of how to use it at least. So yeah, all right, I think that's good enough. We know, we have an idea of how to use it. We're going to use deep speed strategy, and we're going to learn about the config at some point, and then what those different stages are. Right now it's like 0 is off, 1 you do the optimizer states shared on the GPUs, 2 you do optimizer states plus some more, and 3 you do even more. So depending on the level of model you're training, 1 it's not that large, 2 it's large, and 3 it's very large. That's a simplified my simplified view on it right now, and then the details are sort of blurry, but whatever. All right, so we'll go back to the initial goal, which was let's go to, we'll make Finetuning Whisper, cd Finetuning Whisper, and we will just do I don't know, we'll do using Huggingface. And then we will go to that tutorial thingy, and we will copy paste and understand like the basics of how they do it. And then we'll see how we can make it more modular and like convert it to PyTorch Lightning. And maybe we can, yeah, I don't know. It's gonna be difficult, I think. But we're gonna make it work, hopefully. Is there anyone in the chat, by the way? And how long is the delay? I'm kind of curious. So, like, can you write now? We'll take the timer. If there is anyone in the chat. All right, so that's 20 seconds, 25 seconds. Let's make a conda deactivate, conda create. How do you do it? Conda create environment. Whisper, lightning. Wait, conda create and whisper lightning. All right, nvim whisper.py, and let's install the packages. I think I have this, but this I don't have. So Pytorch first, maybe. Which optimizer I use? I always use Atom. I know a lot of people use Atom W, but yeah, I think Atom or Atom W is the standard, and I haven't, like, I spent some time learning about how they work, and you know, all the way from like normal gradient descent with momentum, Attograd, RMS prop, and then, you know, Atom, and then I sort of, right from that point I just used Atom, and then I don't really think about it. Yeah, with scheduler, actually, usually I don't use a scheduler. I just sort of search for a good initial learning rate, and then I just train with that, and then I sort of just babysit the model and look when to reduce it. I find that's usually pretty good, but using a scheduler like learning rate on decay is probably a good idea. Yeah, it's live. So let's install the stuff we need. Data sets. And this is what's going to be tricky. Like, how do you... Because, okay, so this is the question I asked on LinkedIn as well. So I was asking, you know, here with Huggingface, they have all of these trainers too, right? They have like sequence to sequence trainer that is a very specific type of trainer for transformer models. I don't think Pytorch Lightning has that. It just has a general trainer. And, what we want, I think PyTorch Lightning is more general and better than Hugging Face because that's not their primary goal. PyTorch Lightning was built for that purpose, whereas Hugging Face has just sort of tried to integrate it with their purpose of, sort of sharing NLP models and data sets and so on, and making that really easy and accessible. So, ideally, we would not want to use this because, first of all, we have no idea how this works. It's like even if you go to the source code of these things, it's very unclear. So what we would like to have is PyTorch Lightning that is general and modular, and we just use Hugging Face in our, and integrated with PyTorch Lightning. And, I think that might be really difficult. But I will give it a try at least. Okay, conda. We don't have it. Pip install dataset. Maybe we can just do pip install datasets. And this, I think this is for audio loading. This is also why I like Linux. You wouldn't even be able to run this on a Windows machine. And same with a lot of other libraries. I remember I was doing a key point detection project, and doing that on Windows was impossible, like to get the packages for it. We don't need Gradio, I think. And also here, we wouldn't want to, well, I guess, but I would want to know how you do this dataset loading, right? This is nice, and we can just load it using Hugging Face, but you want to have a general way of doing things so that how does this actually work? And then I feel like it's just going to be long term, it's going to be more of a hassle because you're going to run into issues and you have no idea what to do. See what I mean? Like, how does this actually work? So we, for example, for audio here, how are they loading the audio? Or even for images, like the image folder one they have here. All right, we know, like I know how image folder works using just normal PyTorch. So I guess they just do that in some way, but I would like to see the code for it. So how do I do that? just confusing. All right, PyTorch Lightning load dataset custom. So okay, like, it's nice that it's doing all of that stuff for you, obviously, but I don't think the code for it would be that difficult. So I would like to just see the source code for it, and then if I run into any issues, I know how to modify it. Because like here, okay, here we're importing a specific data set, right? And like we need
Hello,
to.
my name is Benelin,
Oh,
and in today's
there we
video
go.
I'm going to show you how you can this command. You see the result of use, and I'm token type.
So we use like a normal PyTorch custom data set with the get item, and then what does he do? He does a lightning data module with the setup and data loaders. Yeah. So how does the custom dataset class look like for loading audio? That's the question. I mean, I guess it's not difficult, right? All we want to do is say we have a folder. Let's say we have a CSV file where we have the MP3 directory of each of the files. And in the CSV file, it's lagging. Is it lagging for other people as well? I'll check it. In the CSV. But yeah, when I think about it, it really shouldn't be that difficult, because all we're wanting to do is literally load, for Whisper, all we want to do is have a transcription, and want to have the audio file. So we'll load the audio file using some library. We'll do this get item. We'll return the audio and the transcription, and then do a Lightning module, data module, and set that up. That way we can make it custom, and we don't have to do this, which I have no idea how it works. And if we go here, it's not even possible to integrate this, right? Or maybe it is, but I don't know how to integrate this into a data module. Maybe it's easy. I'm not sure. All right, we can remove. I wonder if this is best to do in a Jupyter notebook, maybe. Because we're gonna be, to load the data is gonna take some time, like this. We'll just do it this way. How to handle highly imbalanced data set. It depends on the situation, I would say, because in general, you basically have two options, right? First of all, you need to change your metric. That's sort of the first thing I would do, is that a lot of people are working with highly imbalanced data sets, and they're trying to use something like accuracy, which just completely fails, right? Because if you just guess that nobody has cancer, you have 99+% accuracy. So you have to change to precision recall, F1 score, and use that metric. So now you have an accurate metric to guide if you're making progress. And then you're going to look at sort of what you care about for that particular application. So in some situations, maybe you want to have better precision than you have recall, but in others, maybe you're okay with having false positives, but you'll increase your recall as a result. So it depends if it's on the situation. And let's say, hypothetically, you wanted to increase your recall, then maybe you would either oversample your imbalance class using, as you said, weight random sampler, or some other, that's the go-to, for me at least. I don't know if there's other ways to do it. And then, or you could just increase the weight of an incorrect classification of that class. hopefully that gives you some ideas. That's sort of my thought process on it. Let's take another language, I think. Swedish, maybe, if it exists. All right, so it sv.se. Like, there's also, I looked, like when I've looked through this Huggingface Whisper fine tuning, this is I get sort of some warning signals, I would say, because, so first of all, in the Whisper paper, they talk about how, you know, these models are incredibly good at adapting to a specific data source, and they learn the pattern of the dataset source rather than the task itself. That's why they evaluated using zero-shot performance to actually see the generalizability of the model. But if you look at this sort of Jupyter Notebook here, what they're doing is they're fine-tuning on a very particular data set, and the results that we get here is that, all right, we get that the training loss decreases. All right, that's good, right? So we know that it's able to overfit on the training data after 12 epochs, using only 8 hours of training data. Then we see the validation loss. All right, what are we expecting, right, in general? All right, here they're increasing the validation loss. So we're starting from 0.3 and then we're going to 0.46. Okay, then the VER, right? That's the metric we're using, which is, what is it? Like sequence alignment, string manipulation to see how many edit steps it takes to modify one string to another. All right, so we get 34 in the beginning, and then we reduce it to 32 on the test set. But I don't think that's actually any improvement in the actual performance. So there's a very small improvement, first of all, on the actual data set source itself, which is exactly the same source we're training on, which is what they warned about in the paper, but the validation loss increases. So, all right, like I could be wrong in that maybe the validation loss doesn't say anything here for some reason. But the fact that they write this incredibly, I mean, this is a huge notebook, and it's the only way to fine-tune Whisper right now. Like it's the only way I know, at least, that's available. It's through Hugging Face. And so they make this like really long tutorial on it, but it's not clear to me that that it even works. And the fact that this is not something that's even discussed, like for me, this is something that stands out pretty clear, because this is not what we're expecting. I mean, training loss decreased and validation loss should decrease too if we're actually generalizing. But here we were ignoring that. So, I mean, at least they have to mention why we're ignoring it and so on. But it's kind of like, look at this amazing notebook. Look at how easy it is and how amazing this is. But then when you actually get to the details of it, it falls apart. What does the Whisper model do? So Whisper is I made a video on it as well, but Whisper is a sort of the state-of-the-art speech recognition model. So it takes in some audio of a person saying something, like ask now what your country can do for ... and it converts it, it sends it through an encoder, and it tries to then say, give a transcription of what is being said in this audio. And it's a state-of-the-art, like it's performing as good as human transcription, basically, and it's multilingual, and it's the performance differs a little bit about depending on the language, but it's a lot better on English and Spanish and French, for example, than Chinese maybe, or something, or Mandarin. But yeah, they outline it in the paper, but that's basically what Whisper is. All right, so let's take this, and we want Whisper tokenizer. We'll do language Swedish, and we'll do the tiny one. So there's different versions of the Whisper model. There's tiny, small, tiny base, small, medium, large. Could it be that their split into train val is not optimal? so that we see train loss falling and validation when increasing. That could be the case, right? But then why is there a discrepancy between the edit distance that we're seeing as a metric in this case and the validation loss? So why would the validation loss be increasing, but the performance metric we're using is improving? That's kind of like saying the accuracy is getting better, but the loss is increasing on like a classification task. And I mean, at least, my critique is that you need to at least explain this, right? You can't just ignore this and say like, hey, our best VR is 32%. That's not bad, and just ignore all of the red flags. Because I don't know if this is basically, I'm not sure what this is telling us. Is this good? Is this bad? Why is it like that? Fib asks, hi, I'm new to ML. I want to know if I should start by Pytorch or Pytorch Lightning. Pytorch, use Pytorch first. So go through Pytorch and then see how you can use Pytorch Lightning as a wrapper, I would say. Yeah, this is 0.0002, 0.46. I don't know. That's huge. Also, and also I'm curious, like, what was it at the beginning, right? If we evaluate the VER just from scratch at step 0, maybe we can do that actually. We can replicate this and we can see what's the VER in the beginning. Did we actually make an improvement? Could also be the case that we're in the beginning making a degradation in performance, and yeah. How much time does it take to be good at PyTorch? I think that it depends, obviously, but I think you're always going to have things you're bad at and you're wanting to learn. I still consider myself bad at PyTorch, to be honest. And I think you should just go on your results when it comes to your projects and stuff. So imagine, just go through the docs and tutorials and just get a sense, and then build your own project and develop and progressively make more difficult projects, and you'll get better. I'll be right back. Can you share your coding tools IDE? I see you're on a MacBook, but you SSH on a server. Yeah, that's my setup now. I use Mac. I like the user interface. I think it's pretty clean, but doing deep learning stuff, you need to have a Linux machine. So I have a server and I SSH into it. And I think the best ways to SSH is to use either VS Code or something like NeoVim, which is what I'm using here. But I'm still learning about it, so we'll see. I'm pretty bad at it right now, but that's my setup. And NeoVim with Tmux, which is pretty nice. You can detach, then reattach, and you're back at it. Have I tried YOLO V8? No, I haven't, but I've seen a lot of people make videos on it now as well, on how to use it on custom data sets. I feel like the YOLO world has become kind of a mess a little bit. Like the original developer is not the one making any of the YOLO. Like you would imagine that YOLO, they're built on each other, but they're actually like a tree of different research teams or companies that build on it, and they're not even working on each other's work. It's just sort of the latest one was YOLO V7, and maybe that company built YOLO V4 and then they build YOLO V8. You know, it's not like a progression that way. So that leads to confusion in that some people argue that YOLO V5 is better than this version, and you're kind of confused as to which one to use. So one thing to keep in mind is that when I don't know how, I think YOLO V8 seems pretty good though, from my very brief look at it. But it would be cool to do some projects. Maybe I can do that on stream as well. We can go through some, if we come up with a good idea of a project with object detection, then YOLO, we could use YOLO V8 for that. What's my machine learning config? I use Ubuntu 22.04, the stable version, and it's with two 3090 GPUs. So that's my setup now. I just got the second GPU, which is why I'm learning about PyTorch Lightning in the first place, because I realized now I'm going to have to learn how to do this multi-GPU training in an efficient way. And then, yeah, I think PyTorch Lightning has other advantages though. I've just sort of pushed it aside and not decided to learn about it, but I think it's definitely worth it. If you're a beginner, I don't think you should jump to PyTorch Lightning, but learn PyTorch first, and then when you're starting to build your own project, then look into PyTorch Lightning, I would say. And not just sort of learning project, when you're actually wanting to do something and maybe even think about getting it deployed. Is GTX 3090 a good to start? So I would look at this here. This is the latest post. This is the go-to guy for any of your questions of hardware to buy. Like, he has amazing really comprehensive blog posts on what you should focus on the complete setup, from your CPU, from hard drive, to which PCIe lanes should you, like, is it important which ones you have, how important are tensor cores, CUDA cores, like what should you focus on, and also, so he has like, let's see, So he has like raw performance ranking of GPUs. And let's see, on relative performance for the dollar. Let's see. So here we have, so here's the 3090. It's here, which is good for 16-bit training and inference. And it's higher relative performance than the 4090. But then you look at 8-bit inference, and that's a lot better on the 4090. And where's the 3090 Ti here? I don't know. 3090 Ti. There it is. So the 3090 Ti is worse than the 3090. But I would say look through this blog post, and he even has a GPU recommendation. So are you organization? No. Are you training stuff? I would guess yes. Are you training transformers? Yes. Are you? I mean, this is, I'm assuming I'm talking for you now. So you should buy a RTX 4090, but let's say you don't have that money, you should buy a used RTX 3090. And a used 3090 is not expensive. It's like $800 to $900, I think, for a used one, or a used RTX 3090 Ti. And if you want even more cheaper than that, he says, sorry, do something else. Reconsider your career path. No, I maybe you can do like you can work from online or something, like rent GPU whenever you need something that's higher capacity, and just run on a really cheap GPU on your local machine. I'll link this for you. But I think he wasn't impressed that much by 4090, the performance. How much time do I spend a day coding and learning? It depends. Like, you have times where you're really passionate and doing something that's really exciting, and then you spend a lot of time, and then you just kind of get really tired of it and you focus on something completely else for a little bit. But I think on average, I would say maybe 6 hours. Like, and consider those are hours that are efficient, like well spent hours. So I don't know if you're familiar with deep work, but I think that approach to learning is the best. All right, I feel like I'm procrastinating starting with this because I know this is gonna be a pain in the ass to do. But I mean, if we can do this, it's going to be awesome. And this is going to be pretty cool if we can get this to work. I am planning working 4 hours a day after 9 to 5, but don't know if it's realistic. Yeah. It could be realistic for a short duration, maybe, but long term, definitely not. Maybe it would be more realistic to have your 9 to 5, assuming it's not as mentally taxing as working on a machine, like coding and machine learning is. And then on the weekend, maybe spend a few hours. It depends. All right, let's continue then. Let's go. We'll do, we did the feature extractor. And so, all right, so Whisper here, what they've done is they've done a feature extractor. This is for the audio. And if we go to it, we can see what it does, I guess. So this is basically extracts the MEL filter. So it's doing some Fourier transform stuff on the audio. It's just on the CPU. Then we have the Whisper tokenizer, and I think this just inherits from GPT-2 tokenizer, I believe. And they use that as pre-trained. And then we just tokenize it, and now we need to get the actual model and stuff. And Hugging Face has also combined it into a Hugging Face processor, which does both of them. So you have the tokenizer and the extractor in one place. This is not needed, but I guess they say it just we only need to keep track of two, the processor and the model. And then we can print an example, and we can remove all of these things. All right, let's clean this up a little bit. Whisper, tokenizer, Whisper feature extractor, and then remove those. All right, so we have an array of the audio, and then we have a sentence. So if we're gonna make a custom data set for this, our get item would return an array and the sentence for that array. Or I guess, yeah, that would be it. So we'll do that later on, but right now we're just gonna replicate what they do, and we're gonna do exactly the same as if you watch the previous, we'll do exactly the same as we did on those streams, where we took code and we tried to reconvert it to Pytorch Lightning. All right, prepared data set here. So what they want to do here is basically to this thing here, cast column, is a Hugging Face dataset that takes audio and it resamples the audio to sampling rate 16,000, but it does it on the fly, so it's not pre-processed and everything is resampled and then it does the training. So it's going to be unnecessary compute basically. Here on prepared dataset, when we do this batch of audio, it loads the audio and it does this cast column thing. So it converts it. And then here we do the feature extractor to get the Fourier transform array. We do it into a certain sampling. We set the sampling rate rather of the processor. And then we take the input features of that. And so we then have our batch of input features and our batch of labels. I don't think this actually does it for a batch. It's an example, I think. We can print and see, but I think that's how it is. And then I guess they map it. So we pre-process it by like this. We pre-process it by mapping it. We remove the column train. Okay, and then we do multi-processing with numproc. All right, so we have, let's let's print what that does. It's gonna do it run just for a single example, I think. But it's a little bit confusing that they write batch here, I think. Numproc must be an integer. I wonder what this is. Attempt to get length of local prev line. Compute start. I think there's a... All right, so there we go. We have, see, this is one example. So I do think we should change this. This is one example. And this would probably be better. I don't know, like, what do you guys think? Do you, when you're working, are you working on a Jupyter notebook? Because now, ideally, I think you wouldn't have this structure though. Ideally, you would have a get item that is quick for a small data set, and then you would be able to iterate on the entire thing quickly instead of, because I don't think you want to work and train models from a Jupyter notebook. I don't think that's ideal. But usually I just use notebooks for data visualization and stuff. And this is super slow. Let's improve. It's gonna cache it, so I think we only need to do it once. What's up, SLT AI? Where do you work? Well, right now I'm completing my master's degree, so I'm doing a thesis, and then I'll do some side consulting work. But to be honest, right now I'm just mostly excited to build a project and really just develop my skills and learn libraries like Pytorch Lightning, Huggingface, and deployment, so that I can elevate my skill level and just be able to, produce better and just do more complex and useful project. And share that too. I like making videos that can be useful for other people. And, I said that on a community post yesterday on YouTube. What you guys think about streaming? Streaming is sort of just a chill way to, like, for now, like if you just want to combine chat, see what I'm working on. Because I'm going to make videos on this, I think, later on. So my thesis is about graph neural networks and the use of graph neural networks in combinatorial optimization. Basically, how. So this is just getting started. So it's going to be for the next months. But so there's a lot of potential in, approaching NP-complete problems using machine learning, where we might not reach an optimal solution, but we could hopefully reach a suboptimal one that can be good enough, that's fast, as we can utilize multi-GPUs and things like that. I think many of the algorithms right now in that area use, more classical optimization methods, and we haven't found the way to effectively use machine learning. We haven't had a breakthrough in that area. And there's 100% going to be in the upcoming years, I think. Just looking at papers like, what was it? Oh, I forgot the paper for it. The one that came out from DeepMind on the matrix multiply. What was it? Matrix alpha tensor. Yeah. So alpha tensor, it's not really the same thing, but it really opens up the idea of using machine learning to fundamentally find these algorithms that can be much better than the ones we've come up with. And this is probably the biggest paper for last year, probably one of the most impactful papers. So for example, like here you have Stratton's algorithm for multiplication of, I think, 2x2 matrices. And there's a standard way to do it, which includes having how many? 8 plus 4, so 12, I guess. And here we have 7 plus 4, so 11. So one less multiplication to compute the full resulting matrix. And first, if you're not familiar with this, you'll be like mind blown, like, wait, there's no way that's possible. You can only do it, you can only matrix multiply in one way. Like you multiply the first row with the first column, and then you do first row, second column, and so on. But there's actually a much better way. And I think the cleanest example of this is, let's say you want to compute a squared plus b squared, or plus 2ab plus b squared. This is this is one multiplication, one multiplication, one multiplication, right? But you could also write it a plus b times a plus b, right? And this is just a single multiplication compared to the other one. I guess that's 2. This is 1 and this is 3. So I guess it's the same thing for this here. And the alpha tensor found, I believe it was here, this algorithm was what it found. So for a lot larger matrices, that's like 20 or 30% here. Yeah, 20 or 30% more efficient, which imagine all the compute we're doing on matrices, and it's 20 to 30, like just imagine that improvement, and the energy savings and the time savings and if you compound that over all the people running stuff, it's insane. This is super slow. We need to have a better way of doing this. There is a way of doing, when you load a data set, you could do, wherever it is here, streaming equals true, and then it does it. Why is it doing this? I don't understand. Okay, nice. So this way it would be, instead of pre-processing and saving the cache and stuff, it would stream it and then do the pre-processing on the fly, And obviously that's the most general way. Right now, this is not, because imagine you would have terabytes of audio. I mean, it's not, you probably don't want to pre-process everything, write it to disk as a cache, and then load the cache. You would probably just find an efficient way of loading it on the fly. Do you guys use this typing thing? I don't know why I've never gotten used to doing it that way. Like seeing all of this, I mean, I know it's probably a lot better, right? That you can see that, okay, it's a list of dictionaries where the dictionary's string and the value is a union of either a list of integers or a torch tensor, and it returns a dictionary of string and torch tensor. Yeah, maybe that's good, but it just looks messy to me for some reason. Maybe I should learn how to use that because it's probably a good idea. This is what's nice with NeoVim. I can just be like, this code, it looks pretty awful. It's badly formatted. And I can do this. Bam. It doesn't change the comments though. Like here, the comment is too long. You would want to split this on maybe 3 lines like this. This is more readable. Oh, I messed it up now. Oh, yikes. Oh no. Oh no. What did I do? Oh no. Oh god, if this is the case, we're gonna do the streaming thing. We cannot wait for that to do it all over again. I don't have the time to wait 15 minutes. Oh god. I appreciate the kind words, Jimmy. Oh no. Okay, let's do the streaming thing. This is not what we're gonna do. We cannot wait for this shit. This is so dumb. Imagine waiting 10 minutes every time to load some data. Alright. I mean, it's gonna cache it, but anyways. Load data set up here somewhere. There we go. Streaming equals true. Let's see what happens if we stream it. Error. There we go. So here's one thought, by the way. Here we see that the common voice dataset here has 42 hours of data, and it's 50 hours in total of 755 speakers. How is the training and validation split? Is it split for different people, or is it the audio clips that are split into validation and training, so that we have the same person saying different lines and we're validating on the other ones? Because then basically we might have just trained the model to be good at that particular person, and that's why we see a decrease in the or an improvement on the validation performance, right? All of these are things to keep in mind so that when we're reading this, we should be a little bit skeptical of, you know, if this is good or if it's even working actually. But the cool thing is that anyways, if it's not, I mean, we are training and we can make it train. So the thing is just you need to be careful on the specific task. Okay. Yeah, maybe that's streaming. Thanks for the help on that. Should be of type dataset. On the remove columns thing. We don't have to remove the columns though. We can do this. We can keep those for now. I think we'll remove them later on, but right now it's probably fine. But I think we might need to convert our data set to another format. Right, and we need to shuffle it too, I guess, with a buffer size to make sure that it's Does Whisper work with anything else other than speech audio? How about environmental audio? What do you mean environmental audio? Or what would you want to, I mean, it gives you a transcription of what's being said, but fundamentally it has understanding of audio. So you can, I guess you could change it to do classification and different types of things. I'm not familiar with what you mean by environmental data or audio. A triple data set. Maybe that's the problem. So now we're doing cast column here. Maybe that's, let's just not do that first of all and see if that's the issue. No. Wonder how much work we're gonna put into this, because we're anyways gonna convert it back to. All right, let's just. I don't want to do it this way anyways. I don't want to spend time learning how to do streaming on this, because we're anyways gonna do it using Pytorch Lightning. But on the other hand, I don't want to wait for that long. Fuck it, let's just do that. We can read at the same time. Just unfortunate that I accidentally closed the... because after we've done it once, it's going to be fast, so... because it caches the results. But we're going to have to figure out how to do that with streaming. But I'm just thinking it might not be worth it to learn how to do it with Hugging Face now, as we're anyways going to do a custom dataset loading and then convert that to a data module with Lightning. So... okay, so here they do the self.model, they import that as a Hugging Face one. They do metric also from Hugging Face. They compute how, or they write how to do the training step. Live check. And then we do, so training step, and we specify validation and all of that. And then configure optimizers. Cool. So they actually do that with the configure optimizers. They actually do the scheduler here. Maybe that's the way to go about it, but yeah. Let's see what else. So I mean, it seems to be pretty easy to integrate it. I'm just wondering how you specify when you have a sequence to sequence, because we're gonna have a sequence to sequence trainer, right? And like, what's that in? I don't think that even exists, does it? There is? Okay. Yeah, no, yeah, that's Hugging Face. So sequence exists in Hugging Face. But you know, we don't want to write, I don't want to jump between libraries. I think Pytorch Lightning is the way to go for training, and Hugging Face is the way to go for getting the models for the, like, for NLP projects and data sets maybe, and metrics and all of that stuff, right? Right, Pytorch Lightning has been, like, they wanted to do one thing, And that's training. Hugging Face was, I feel like they have started to integrate that, but it's not their sole focus. And I think this can be a little bit confusing which one you should use here, right? But that's what I'm trying to do. I'm trying to learn how to integrate Hugging Face with Pytorch Lightning. But we need to learn then how this works and how we're gonna set it up. And specifically that would be, yeah, I mean, computing the loss, I guess, and doing a training step. Hopefully it's not too difficult to find how to do that, but we'll see. It might be challenging. Okay, we've implemented, or we copy pasted the data collator. So we take input features, we do a padding of those input features. Okay, wait, we run it through the processor and the feature extractor and pad them, I guess. And then we run it, I'm not sure why we're doing that pad here. Oh, okay, so I guess the feature extractor returns maybe different shapes depending on the length of the audio. And then we need to, okay, so it might not be 30 seconds, right? So we're padding it to all have 30 seconds of audio. And then we are tokenizing it and we are padding it. And we're filling with an attention mask. And then if beginning of sentence token is a pendant, we cut it so that the labels are one step in front of the thing we're sending in. And then we're returning the batch. And then we initialize it. Then we import a metric, WER. Like that. We compute the metric. Okay, and here's the actual model. So we're gonna change this to tiny as well, tiny. And so we're doing Whisper for conditional generation from pre-trained. This is our model that we send in. I guess this is the entire thing. So we send in the, oh, it does? Well, that would be awesome if the model itself computes the loss. I was thinking maybe we would have to do that part ourselves, which could be error prone and not very nice. But yeah, I guess you're right. It could do it. We'll see what it returns, I guess. It returns a forward of the model returns returns example. Yeah, if not, yeah, it's true. I mean, this is okay. So this is, I guess, not that difficult. It's just a cross entropy loss, and we're just doing this. Yeah. So yeah, that's good to know. And so that's nice. So we have the model. Let's see. All right. So this is the training and this is the validation. All right. So we should have this cache now. And then, oh, no. All right. That's fine. Let's just not look at that. And I don't know what this is. Forced decoder IDs. None. Suppressed token. So this is what exactly? I think what this is like you can prompt the model by, I think this is like for having a specific type of prompt in the beginning to the decoder. So you kind of force it to start in a certain way. But I'm not sure on the suppressed tokens. Let's see. Has token IDs that are forced as model outputs before autoregressive generation is started. These tokens control the transcription language and task. For fine-tuning, we'll set these IDs to none as we'll train the model to predict the correct language and task transcription. There are also tokens that are completely suppressed during generation. Suppressed tokens. These tokens have their log probability set to -inf such that they are never sampled. All right, and then we'll do sequence to sequence training, copy paste code, because that's what you do, you know. Either Copilot writes the code or you copy paste from somewhere. And to explain it, you ask ChatGPT. All right, cool. So now we have all of that stuff. Okay, cool. So it's done. Nice. Let's do clear. Let's run this now, and hopefully we're able to train it. But this is, you know, I don't like the setup of this. So if it works, we're going to have to change it one step at a time. So this is what I mean with the loading of the cached. It's already pre-processed now. So TensorBoard callback requires TensorBoard. I think it's probably at the end here. Push to hub, false. Oh, it's actually doing multi-GPU automatically. This is the tiny one, and it's this slow. Damn. You know, I think we're having a data loading issue as well, because as you can see, the power draw is pretty low. So I'm wondering if it has to do with dataset loading. And I don't know, I don't like these error messages. Use cache true with gradient checkpointing. I think probably we should increase the number of workers, right? That would make sense to me. But wonder if we would do, I don't know if we actually want to train this, right? Now it works, so let's just try to modify everything. So that we can do it in PyTorch Lightning. Oh. I like that Lightning automatically warns you. I was just curious if that's the issue we're running into as to why it's so slow. Yeah, it's a lot faster, right? I think so. And if we look at the GPU utilization, it's larger, but still not ideal. Maybe increase the batch size or stuff like that. But all right, let's, as this is work or training, we could start setting up our Lightning setup. So what should we do? I think we should start probably with the dataset loading. I'm just kind of wondering a little bit what we will use, because Wow. Okay. 21 gigabytes. Hey man, how many lines of code do you suppose a multi-class text classifier would have in general? From scratch, or if you would use, you know, and are you talking like training wise, or the model, or so inference, not training? I don't think it would be that much. Probably. I mean, okay. So let's see. Here we trained Whisper, right? This is 168 lines of code. You can probably do something similar for text classifier. And that's training. For inference, you can probably do it in like 3 lines. Yeah, that would be my estimate. Probably around 200 or so. But I think lines of code is not that great of a metric, because it's really about the complexity of what the code is doing underneath and the potential of errors that could be when training. And if you were using that as your sort of, if you just want to minimize lines of code, you could probably do it in a lot less, right? But if you're just talking about like what's the size of the project, and then that's probably a good rough estimate. All right, let's say we were just to download this. Recorded hours 1, validation, just a small. Do I need to write my email and stuff? All right, fine. Let's do that then. How do you do this? I forgot. SSH. Oh, SCP. So we probably restructured this. So we want to have a CSV file where I guess we can just take, we can probably use that maybe. So we want to take this data set here. I wonder if there's a smarter strategy than doing this. You can just use Huggingface load data set, but how do you create a loader from that? It's not clear to me how, right? Like here, you do everything in here, but you load a data set. So here we have the name, I guess. And if we look at here, we have common voice SC. That's not the actual audio file, is it? No, here it is. Okay, so that's just something else. That's the audio file and that's the transcription. And then they have other data as well. But we'll just load that in our data set thing. So we can ask Copilot, load. We have folder. We have, what is that we want to ask it to do even? Create a Pytorch custom dataset that loads data import image. We're not going to need that. And it's trying to do an image data loader. All right, let's remove those, and we're gonna want to do just this for now. Just data directory, load data. Let's see, path. Oops. Okay, let's stop this. Unmatched. It's it doesn't integrate well with black for some reason. Let's see. So now we have the data set. We're printing it. So hopefully it will be. Oh, column name 0, 1, 2. Okay. Okay, so we have that now. Now we just want to load. So for if we have a single example, it's like index 1, we want to print get row index for column path and sentence. All right, so we have the audio file and we have this. Now we can probably do, all right, let's just start that way. So we'll do path is ospath.join of clips No. Audio file path. Audio file path. We don't have to do this. All right, so we have data slash clips slash the audio, and then we have the sentence right there. And so I guess that should be good enough, but we have to load the audio, and I'm not sure. I'm gonna need to fix that at some point. There's some error with the LSP, and I think how it integrates with Black. So what are we doing here? We have the full of the path to the audio, and we have the sentence. Now we want to, I guess, we want to load the audio, and we want to transform it using this feature extractor, I guess. And then we want to create a data module with Lightning. I wonder if I'm doing extra work that's not necessary here. There should be some good way of loading. because it's gonna get messy. I think we're gonna have to do, I guess we're gonna have to do that anyways with the collator and stuff, because here we have, maybe it's not too difficult because this is already when we've loaded it, so then we're padding it. I mean, we have to do this anyways, so I guess no big deal, maybe. Yeah. Yeah, I'll take a little bit of a break. I'll be right back though. Wondering what kind of task we can do it on, because it would be cool to, when we get if and when we get this working with Lightning, then maybe it would be cool to do like fine tune it on some particular type of tasks. That would be pretty cool. And do a project. I think that would be pretty awesome. I'll have to think about what we can do with it though. That would be fun. All right, I'll be back. Take a little bit of a break. But I don't think it won't be that long, so I don't think I'll stop the stream. I'll just, yeah, I'll be back. Like, I posted this on a YouTube community post about how people thought of, let's see, like what people thought about Chat GPT replacing, no, wait, sorry. Yeah, ChatGPT is replacing Google search. And I think a lot of people said nah, but like, I think if I redid it, a lot of people would say yes, because there's, for me, I Google a lot less with Copilot, and I also use ChatGPT for a lot of things that I would usually Google. And I wonder how that's going to be in the future. Imagine it's just going to increase in the ability of it, and like in the future you might just have a ChatGPT as your sort of best friend that knows everything, kind of. I don't know what I think about this epidemic sounds. I mean, it's pretty nice. You can use these on, but I would like to just have a nice playlist. Because I don't think you can use, I don't know. I mean, I'm not monetizing streams anyways, but I wonder if I would get like a flag if I would play Spotify or something. Yeah, I saw this yesterday that Google had cut 12,000, which is 6% of the 6% of the people on Google. And I read this, which was pretty damn insane. I felt like I guess it's pretty impossible to find now. Yeah, this week has been hard for people in tech. 10K layoffs at Microsoft, 18 at Amazon, 12K at Google. Yeah, I think takeaway is more that everybody can get, I mean, yeah, don't let your job control your life. I don't know if, it's difficult. But the post that I was looking for was a guy had worked 16 years for Google, and he basically got an email like, you're laid off, and that's it. Oh boy, I'll find it. It's gonna be pretty hard to find. Whatever. But anyways, he had been let go, and he got to know about it by an automated account deactivation. Like this. I don't have any other information, as I haven't received any of the other communications. The boy replied, "You've been let go website. It was a largely wonderful 16 years, and I'm really proud of the work that I and my team did. This just drives home that work is not your life, and employers, especially big faceless ones like Google, see you as 100% disposable. Live life, not work." Yeah, I would also be pretty frustrated about that. I think I like Twitter more than LinkedIn, and I feel like it's starting to stabilize now a little bit, and that people are maybe realizing that Twitter is still gonna stick around. A lot of people were leaving, but I don't know. I like that they're doing a lot of things fast, and that they're iterating, bringing in features like the views and stuff. All right. Well, let's see. So what's the goal here? Let's write down what we actually want to do. Data set. Goal. Let's see. We want to create. So the overall goal, right, is to rewrite the code Pytorch Lightning, and now we gotta to do that, we gotta load the data set. Then we gotta using Lightning data module. And that's pretty much it. But to do this one, let's see. Because there are multiple ways of doing this. We could either, let's see, do it as we are now, maybe integrate Huggingface loading data, or we can write it ourselves and use Lightning data module. I think we're gonna go the step that we did, and then I think the model stuff will be relatively easy. I think actually the data loading will be the most difficult, and then it would be cool to apply this to our own project. Like, I don't know exactly what we can do. Let's see, so we would fine tune that would be the end goal of this. I'm just taking a little bit of a break. I'm gonna get some lunch and then I'll get back to this, and this is what we'll do probably in these steps here, and then maybe see if we can use sharded training with Lightning. I like part of this. I listened to this, and obviously I listened to this one.
It's very interesting to
This
think
was
about.
pretty nice. I haven't listened to all of the parts though, I think.
So aside from the teaching you're doing now, putting out videos, aside from a potential Godfather Part 2 with the AG at Tesla and beyond, what does the future for Andrej Karpathy hold? Have you figured that out yet or no? I mean, as you see through the fog of war, that is all of our future, do you start seeing silhouettes of what that possible future could look like?
The consistent thing I've been always interested in, for me at least, is AI, and that's probably what I'm spending the rest of my life on, because I just care about it a lot. And I actually care about like many other problems as well, like say aging, which I basically view as disease. And
Ingen fara. Got you. I got you. All right, we're ready for round 2. I got my smoothie.
I care about that as well, but I don't think it's a good idea to go after it specifically. I don't actually think that humans will be able to come up with the answer. I think the correct thing to do is to ignore those problems and use solve AI and then use that to solve everything else. And I think there's a chance that this will work. I think it's a very high chance. And that's kind of like the way I'm betting, at least.
So when you think about AI, are you interested in all kinds of applications, all
Yes.
kinds of domains, and any domain you focus on will allow you to get insights to the big problem of AGI?
Yeah, for me, it's the ultimate meta problem. I don't want to work on any one specific problem. There's too many problems. So how can you work on all problems simultaneously? You solve the meta problem, which to me is just intelligence. And how do you automate it?
Is there cool small projects like Archive Sanity and so on that you're thinking about? The world, the ML world can anticipate?
There's always like some fun side projects.
Yeah.
Archive Sanity is one. Basically, like there's way too many archive papers. How can I organize it and recommend papers and so on? I transcribed all of your podcasts.
What did you learn from that experience, from transcribing the process of
So he's talking about Whisper.
like consuming audiobooks and podcasts and so on. And here's a process that achieves closer to human level performance and annotation.
Yeah, well, I definitely was like surprised that transcription with OpenAI's Whisper was working so well compared to what I'm familiar with from Siri and like a few other systems, I guess. It works so well, and that's what gave me some energy to like try it out, and I thought it could be fun to run on podcasts. It's kind of not obvious to me why Whisper is so much better compared to anything else, because I feel like there should be a lot of incentive for a lot of companies to produce transcription systems, and that they've done so over a long time. Whisper is not a super exotic model, it's a transformer. It takes Mel spectrograms and it just outputs tokens of text. It's not crazy. The model and everything has been around for a long time. I'm not actually 100% sure why this came out.
It's not obvious to me either. It makes me feel like I'm missing something fundamental.
I'm missing something.
Yeah, because there's huge, even at Google and so on, YouTube transcription.
Yeah.
It's unclear, but some of it is also integrating into a bigger system.
Yeah.
So the user interface, how it's deployed, and all that kind of stuff. Maybe running it as an independent thing is much easier, like an order of magnitude easier than deploying to a large integrated system like YouTube transcription or anything like meetings, like Zoom has transcription. That's kind of crappy. But creating an interface where it detects the different individual speakers, it's able to display it in compelling ways, run it in real time, all that kind of stuff. Maybe that's difficult. But that's the only explanation I have, because I'm currently paying quite a bit for human transcription, human caption, annotation, and it seems like there's a huge incentive to automate that.
Yeah.
It's very confusing.
And I don't know if you looked at some of the Whisper transcripts, but they're quite good.
They're good, and especially in tricky cases.
Yeah.
I've seen Whisper's performance on super tricky cases, and it does incredibly well. So I don't know. A podcast is pretty simple. It's like high quality audio, and you're speaking usually pretty clearly. And so I don't know. I don't know what OpenAI's plans are either.
But yeah, there's always fun projects basically. And Stable Diffusion also is opening up a huge amount of experimentation, I would say, in the visual realm and generating images and videos and movies ultimately.
Yeah, videos now.
And so that's going to be pretty crazy. That's going to almost certainly work, and it's going to be really interesting when the cost of content creation is going to fall to zero. You used to need a painter for a few months to paint a thing, and now it's going to be speak to your phone to get your video.
So if Hollywood will start using that to generate scenes, which completely opens up, so you can make a movie like Avatar eventually for under $1 million.
Much less, maybe just by talking to your phone. I mean, I know it sounds kind of crazy.
And then there'd be some voting mechanism. How do you have would there be a show on Netflix that's generated completely automatedly?
Potentially, yeah. And what does it look like also when you can just generate it on demand, and it's and there's infinity of it?
Yeah. Oh man. All the synthetic content. I mean, it's humbling because we treat ourselves as special for being able to generate art and ideas and all that kind of.
All right, so let's do a data set then. We will try to just .py, boom. We got a simple loading here. We will try to load this as audio, and then convert it to a data module with PyTorch Lightning. I'm not sure how you load audio though. I don't know what the best way is. Could not convert string to int. Oh, let's just print audio here. Torch.load. I guess you can't do torch.load. I was just trying it because that's what. Pi sound file failed. Try audio read instead. I wonder why it failed. So let's do. I wonder if it normalizes the audio in some way too. Because this can be a bit dangerous, I guess. I don't know how Whisper does it. Because they didn't release the loading and stuff. But I guess they do. So wait. If you go to the audio here, we have load audio. We should just be able to do this, to be honest. So we have load audio here, where we input the sampling rate, and they're gonna specify what we want, and also pad or trim, mel filters, and all of that. So it might be a good idea to do it the exact same way. Probably. Right, transcribe, we send in the audio. From the audio, what do we do? Let's see, audio. Log mail spectrogram. So, I mean, we could just download Whisper right from this and then use that part for the data loading because it will be identical as we do as the model has been trained, I guess. Just not sure. We might already do that with, if we go, if we go to Whisper and we go to feature extractor, I think this is already, it's doing the same thing, right? Get mel filters. Let's see, where is it? Whisper, audio, here. So we do audio, numpy array, and we return torch tensor of mel spectrogram. I mean, this is doing something similar at least. So the question is how what we send in here is different. I mean, we send in the audio file here. So I guess we would want to do this thing first where we load the data using FFmpeg. We do the normalization that they do. Probably. instead of doing that, we can try this. Syntax error. Oh yeah, return thing. All right, so what do? Instead of doing that, we read it with ffmpeg. We do output on a specific type of format, which is the format Whisper wants it in, and then we convert it to a mono audio with a specific sampling rate. We can do that, self.sampling rate. And then we're doing MP from buffer, and we're normalizing it. And that's the audio. We can try if that works. No module. Okay, pip install ffmpeg. So one important thing here is obviously that we need this to be fast, because now this might be slow. You know, we're doing conversion of the format of the audio. It might be better to run through the audio, make sure that it is in this format, but until then, let's just do it this way and we'll see how it works. I mean, we'll convert it to a data loader and see the speed of it. But if we just do this, we'll see as well. Yeah, I'll check the requirements, but I think if it worked now, so that's a good idea. Yeah. All right, so I mean, it's, I mean, this is pretty fast, I think. 110, but we're gonna create a data loader and we're gonna see. we're gonna have to do padding. Because they're not gonna be the same shape. Maybe we can just do this for now, but we'll do a collator later on. I'm just curious if it works. That's probably, I don't know, fast enough for a single worker. And imagine it doing all the pre-processing and stuff. We would obviously need to do other stuff here as well. We need to run it on a feature extractor. But as a just simple case here, I think this is pretty good, and we could also pre-process it here as well. Yeah, we'll see if we need to improve it, but at least we got something working here now. So let's see what we can do now. Yeah, so I think that the Whisper model will be let's see. I don't know why it's saying that I got syntax error. Yeah, I'm using Copilot, but also I'm new to it, but like LSP with NeoVim, which has some autocomplete stuff, but you mostly for the other stuff it's Copilot. Let's see, so this should be so there we go. Data feature extractor. We'll run the feature extractor on Oh. Okay, so 183,000. What if we don't pad it? Will it still fix it for us? Seems so. All right, so that's nice. We'll do that. We'll return that as our audio. Wow, okay, that was super slow. That's what's taking all the time pretty much. So all of the time is in the feature extractor. We'll see if it's a bottleneck later on, but I don't think there's too much you can do about that because we will... I mean, you could you could run it through and then load from that, which would be a lot faster because the feature extractor is always going to do the same thing. It's deterministic and it's not trainable. But if you would want to load it on the fly, this is how you would do it, I think. And I think, yeah, let's do print audio.shape here. You could also increase the number of workers here. Maybe that would help a lot. Whoa, there we go. I wonder what we're returning then. Is it a list or something? Dictionary. All right, we're doing can we print shape now? Type. So that's faster, for sure. I don't know how slow or how fast our model is able to run. We'll do a profiler later on when we get everything working. But so let's see, what's the next step? So we loaded data now on that. We're doing the feature extractor. In the collate stuff, what did they do? Data collator. Here, taking input features and they're doing padding. What are they padding then? They're doing tokenization. We need to do that as well. We can start with that. Tokenizer, there we go. right, so we have feature extractor, tokenizer. Let's run the tokenization here. Right, we need to do batch size of 1 because we need a collator. No? 1 shape. Okay, let's do print text and break. All right, so we have input IDs and we have attention mask. Yeah, so the attention mask is always going to be 1. And what about the shape of the tokenization? It's like 25, 30. All right, we'll need to pad that. Yeah, that's what they are doing. Prepared data set. Here doing yeah, we're getting the input features as we are. They're getting the labels with the tokenization. That's what we're getting here. All right. And then they create the collator. Oh, mistake. Oh no. So here, if we do feature extractor.pad input features for the batch, yeah, we need to create a collator function. Create a collator. Huh, okay. We can do that. We won't do the processor though. We'll just do feature extractor and tokenizer. And we will take out just the features, which will I actually don't remember how this worked. So if we do, remember I've done this one time. Machine learning. I think here probably. Here, so call, we get the batch and the targets. So item 1 and item 0. Okay, so we'll do that, and we just get the batch here. Batch. Probably. We'll do start there. Input features, we will want to do, I guess, oh, okay, That's all right. Oh, okay. So this has to, I guess it has to be as a dictionary. Okay, so what's the input? So I mean, this is a list here. We input features here. We take input features of input feature, and then we are taking the batch, cell feature extractor, input features. This is a list, and this is a list. Maybe we can print audio features here, and we'll see. So it's a list of tensors, I guess. Okay, what's the shape? 183,000. I really don't understand what we're padding here. I mean, everything is 80 and 3000. Seems like. And it's a torch tensor as well. Shouldn't we just concatenate? I'm thinking we don't need to do this pad thing, but since we can just, I don't know, maybe let's just torch cat all audio features, which is in the index 1 in batch. Yeah, that's what I'm thinking. And then we should just do the text. And that's pretty much it I was thinking. So this should be a, let's see, print text labels. Oh, we have input IDs, attention mask. Right. Yeah, I think we will need to output here the input features. And this should work. We have 26 and 41 and we just want to pad it. And we pad it now. What? Now we pad it doing masked fill. Yeah, I just think maybe we need to specify the output in a different way. Whoops. Let's see. We need to. Might not be the best idea to change that thing, so maybe we should convert it back to how it was here. Because here we are, let's see, what are we doing here? Input features, we're making a list of dictionaries. So list of dictionaries, where we're doing input feature. All right, we can probably keep it that way, I think. Like this, we can just delete this. And then whoa. Okay. That's not what I wanted. Cool. What about the text here? Doing example of input features. Is this thing okay? And then labels. Input features, feature of input features. We're doing here input IDs. Feature of labels. So I guess we don't have to do that much here. We'll just do label features. Seems pretty dumb to me, but okay. Label features, and then yeah, okay, and then we'll do label batch. So, okay, what is that then? Nothing? Where are the actual texts then? Because everything that's here is just this. But we want to have, what is it? Okay, so we're going through each in the batch, and we are, what are we doing? We have input features as the first element here, and then that's a dictionary, and then we have our input IDs and also our attention mask, which we can skip. So I think we just are just gonna try to take this, but it's a tuple now. All right, so it's a list of dictionaries, which should be what we are wanting, I think. I guess not. Here we're doing a list of dictionaries where we have input IDs equal to that. Here we have a list of a dictionary, input IDs as a list. Okay. And it's just numbers there. All right. And then what did we get for the data set here? Okay, so first of all, it's a tensor, which might not be what we want. Okay, so we need to convert it. Let's see. What if we do? Okay, not sure how they don't get tensors. Maybe it's from tokenizer here. We don't need to return tensor. Cool. All right, that might be it. Now I think it should be the same structure now. We can try it. Tokenizer pad, boom. Nice. All right. Yeah, okay, that's cool. So we did label features with this thing. We did text labels. We have the attention mask, and we have ones or zeros for the attention mask. So that's nice. We have our let's change the name a little bit. So we have whoa, let's see. Boom, go back here. We have audio features. Here we have batch audio. Here we have text features, and here we have batch text, and we will return, let's see, what did we do here? Images and targets, so we'll return this, yeah. And Whoa, what happened? Data set. There we go. Nice. All right. Cool. That took a while. All right, we got it though. Nice, nice. So let's just see how fast it is, because now we got the collator and all of that stuff, and we're padding as well. We need to add the attention mask though. And as you can see, it's pretty slow, but this is with 0 num workers. So it's probably fine. All right, what else? Let's see. So what else? Let's see. If we go to Whisper now, oh, that was a mistake. And Whisper. Here, we're doing masked fill as well. Okay, so we need to let's see. All right, we have all of those and we're padding them, and then we have the attention mask here. Can we do this? I don't know what that .ne is. .ne. .ne. Not equal to 1. We'll set that to -100. Okay, let's print the batch text afterwards, maybe. Oh wait, we didn't actually. It probably didn't work now. Yeah. All right. So the ones that are 0, yeah. I hope that's correct. I mean, there could be errors. I don't know how to, but at least it's padding it to the correct length, and that looks good. So what's next? So we need to make a, let's see, we need to make yeah, so they're all starting with that thing. We'll see if the model is also appending in the example of Hugging Face. Here they, let's see, they removed the first beginning of sentence because it's append later anyways. I don't know where it's appended exactly. I guess in the sequence trainer, but I don't know if we're gonna do that, so. Or we should do, I guess. I mean, we can, let's do the same, because I guess it's gonna be appended in the, I don't know if it's appended in the sequence trainer or in the actual model though. That's the question. Whatever. We'll figure that out, I guess. All right, let's make this into a data module now. Let's see if this makes sense. All right, so we got a lightning module. We're doing data, directory, whisper model, sampling rate, setup, data collator, and then we're creating our loader. So this is obviously not correct because we are just having the train loader right now. Yep, I'm using Vim or NeoVim. Okay, cool. So we're doing data module that's set up. we're iterating through the data loader. We're printing the input features, shape, and yeah, I'm not sure if this should be 1 here. It looks a little bit strange, maybe. These look all right. Yeah, I can explain the dataset path setup. I mean, what we're doing here is pretty general, I would say. I mean, first of all, we're creating our own class here. Here it's a little bit complicated because we are using Huggingface, feature extractor, and so on. So we need to specify the exact way they're doing it, and we're doing some audio loading as well. But in general, right here, you can do your own class, like normal bare bones PyTorch. Just get item for a single example in your data set. This is on the fly, and we are only loading the CSV file into memory in our data. Then, so this data, we needed to do a collator as well, so that when it's batched, we need to pad it so that it's exact same shape for all of the examples. And then what we do is that for the sort of the lightning, the PyTorch lightning stuff, we do the self.data directory. Well, let's see. So we are first doing our init stuff, and then we're doing the setup. So for the setup, we are initializing our data set and our data collator. So here, this is kind of, we're just doing setup of all the stuff we did previously, right? And then all we're doing here is returning our trainer loader, and we need to do the train data set, val data set, and so on. Right now we've only done the training, but that's easy copy paste later on, just to do self.train data set, val data set, and I think that's pretty much it. I mean, one thing we want to send in here too is the batch size. And then you would do self.batch size instead. Hopefully that gave some explanation. So like in general, you could do image data set here, just load your image data set of choice. You don't need to do a collator then. And then all you do is just self.dataset equals. I think there's more functionality this data module does, but that's so far what I'm using it for. And I think all it does really is that we can integrate a lot of, actually, I don't know why we want to do it exactly this way, because the only thing I can think of right now is the batch size, which we can use with the trainer, and I guess we can do callbacks and stuff. But yeah. But now, hopefully, we got the data set to work. I mean, it could be that we need to do some reshaping of this because we might not want to have, I don't know exactly what the shape is. We could check that. So this is Hugging Face. We need to go to, I guess, this here. What is it that they're returning here? So with the collator here, what is batch of labels? I guess. Oh, that's not what I wanted. Okay, that's the same, but we want to have the print label features. Labels batch. Yeah, so I think as you can see here, we have the batch 83,000. So I think for our data set setup here, we would probably like to, it's probably in the here. So for audio feature.shape here, it's probably one additional. Oh. Whoop. Yeah. So if we do input features dot shape, that should work, right? Yeah. So let's do I mean, fine. Let's bring that back. Then we can do it later in the collator, I guess. Shape. Patch audio, that shape. All right, so wait. How are we printing the shape? We're doing batch 0 of Can you say a word about torch squeeze and unsqueeze? Basically, all that the squeeze does is that it can add or remove a dimension. So here, this is a 4-dimensional tensor, right? Where the amount in the first dimension here, or 0th dimension, if you like index it, it's 32 for our batch size. Then we have just 1 here, and then we have 80 and 3000. So I think this is we have 32 example audio files, and for each file we have 80. I think it's like Fourier transform something. I don't know. I'm not exactly sure what this is. And each of those has 3000, which is, I think, related to 30 seconds in duration for the clip. So we've padded each clip to be 30 seconds. Even if it's like 5 seconds, we've padded it because Whisper expects to have 30-second audio. So here, the model is later on going to expect an input of 32, 80, 3000, because this one here is not really, it doesn't give any information, right? It's not any extra, but it's still an additional dimension. So if we index this, it's going to be index error for if we're expecting this one to be sort of 1 dimension before, right? So if we do torch.squeeze here, before we return it, meaning we do batch audio of input features. Let's see, input features is equal to batch audio of input features, and then dot squeeze. And then, so squeeze, we're removing a dimension. So squeeze of 1 here would mean that we are going to remove this 1. So if we rerun it, we should hopefully get 32, 80, 3000. Oh, this should not be like this. And there we go. So now we have the correct shape. And we should be good to go as our setup. We'll do nvim model.py. So we'll implement all the training setup now for our model. So we will do, let's see, let's actually do touch model.py, touch train.py. So this is the Hugging Face stuff, right? Everything is in a single file. Yeah, unsqueeze is to add a dimension. So if we would do squeeze of 1 and then unsqueeze of 1, we would get back the same again. So for example, you might want to do like, if you want to create a batch, for example, you might unsqueeze the an extra dimension so that you get 1 additional dimension for each, and then you might concatenate all of the examples across that dimension, and then you have a batch dimension, for example. All right, let's see. So we have Whisper, boom. And we'll still use these compute metrics and stuff. These will be in, we'll add these later on, but for now we will want to implement the trainer, which will take our model and everything, which will be this. But as a starting point, we could probably start from, let's see, we can do this full screen here, and we'll do model split it, and we'll do here, let's go, we have VAE, which we worked on yesterday, and we can probably take the model here. Let's just copy paste that first of all, and obviously we will modify pretty much everything, but I just want to do our training step, but let's remove that for now, and let's remove all of this as well. All right. Cool. So now we have, all right, the model, we need to do a forward step where we send in, or we'll just do a training step. We'll send in our batch, and I don't know exactly what it's expecting, to be honest. Maybe we can see. This is actually a bit tricky. What do we want to send in here? So we have the model, we've done all the data loading stuff, and now it should be just to basically send it in, right? We have, obviously we need to set up all these things, but but this is tricky too, because we have a generation max length, and I don't know where we send that in. Oh, this might be tricky. Oh no. But actually, that should not be in the training. That should be in the evaluation step, I think. Yeah, that's in generation. I'm pretty sure, because then that's when we want to just evaluate it, and we want to have a cutoff point. But that should not be needed for the training, because everything is fixed in size, I think. So let's see what happens if we ask Copilot. So we take input IDs of our batch. Not sure if we have it set up this way, but we might have. Yeah, I'm not sure about that. We'll see. Yeah. All right, so we have those two, and that's we need to take those out, I guess. We don't have decoder attention mask and this though, so that's a bit confusing. Yo. So let's see, this is not what we're gonna do. I'm not sure how to send into this. We have input features, decoder input IDs. Let's see what we do here. I mean, we have the not sure how we send this. We have input features. Those are the input features. Decoder input IDs. We need to modify those, I think. And then we need to send in the labels as well. So what we send in now are the input IDs. And we need to change to have the labels. And we have the attention mask, which is for the decoder. And we don't have any attention mask for the encoder, I think, because we want to listen to the entire audio, even though some has been padded, I guess. And yeah, I guess yeah, so let's see, we want to get so in our model here, we need to create, let's see, we have, I think like this, and we have, we have encoder input, decoder input, decoder attention, and then we need to do, we should do this in the data though, so this should be here where we do batch text of labels is pretty much that, but whoops, there we go. But with this right here, so copy this over. So labels equals batch text input IDs clone. If labels is equal to the tokenizer, we'll do that. And then we'll do batch labels equals labels. And let's see. So if we're correct now, this should be of input IDs should not be the same as labels. Should be one less. And it's not. Oops. That is a bit confusing. How long does it take for me to make from scratch videos? It depends. Like, this is difficult stuff for sure. This is like Finetuning Whisper, and also we want to convert it to PyTorch Lightning. That's hard, man. So yeah, it depends. Like, some projects go pretty fast. But some can take, like a week. What's that then? If we have a little bit confused over the indices here. So here we're doing BOS token ID, beginning of sentence, right? A bit confusing over BOS token. Oh no, Python Whisper. I'm not that knowledgeable about Bayesian probabilistic machine learning. I've just taken a basic Bayesian introduction to Bayesian statistics course, so I don't know exactly what that is. Yeah, so it's the same here. All right, so what is this? So we're printing what? We're printing I'm not sure what we're printing. Oh, what? It's not even running this thing. Okay, so let's see, what does this actually, what do we want this to do then? So this is doing nothing because the BOS token is not like that's the end token actually. And I have no idea how it got mixed up. I'm missing something. So what's happening when we send into this? We're going here, we're doing forward, right? And what is it that we actually need to send in here? Labels, input IDs. We're computing the loss here, so we don't have to worry about that. And we are sending in what happens if we just try it? Say a few words about implementation of an architecture like BERT or GPT from scratch. I think first of all you need to break it down a little bit. So, for example, GPT, you would see, all right, it's a bunch of stacked transformer decoders, right? So how do you, if you would want to do it from scratch, all right, then you need to break it down. All right, let's implement a transformer from scratch, and let's just take the decoder part. Let's stack those on top of each other. And then and then you check the paper, like how did they stack them, and so on. So I think basically try to read the paper, understand the building blocks, and then try to implement each building block one at a time, and then put them together in a nice way, and then iterate on your implementation to debug, fix the bugs, and all of that stuff, and clean up the code and so on. I feel so stuck now because I really don't want to use Huggingface trainer, but I don't understand. So this is the problem I feel like with like I don't know what's happening here with the sequence to sequence trainer. I feel like there's so many things that are hidden from me. Like, for example, they add these comments: if BOS token is appended in previous tokenization step, cut BOS token here as it's append later anyways. But is that where is that exactly? Where do they append that? And how do I know what this does? Because all right, let's just do Yeah, I might be able to do that in the future, but right now I'm mostly, like, my desire right now is mostly to start doing deployment stuff, and not so much, like, I want to build things that are kind of useful, and sometimes it is beneficial to learn things from scratch. And I might do that sometimes, but that I don't want that to be my full focus. All right, we have learn rate. We're sending that. Non-workers we don't have to send in. Can remove the logger and this stuff first. We have PL trainer. Devices 1. Oh, are you serious? Come on. I'm expecting to get an error on... Oops. I'm expecting to get an error on the model side, not on the data. Mm-hmm. Yeah, so right, it seems that we're getting at least error on the model. Raise, you have to specify either decode or input IDs. Oops. This is lagging for me now. Oops. Okay, the question is, how are we gonna run the model from this? What exactly is the input to this, and how do Whisper do it, or Huggingface? I mean, So I guess it's pretty similar to the lightning trainer. All we have to do here is, I guess, adapt these things that they're doing. So they're doing predict, and then a prediction step. But yeah, I am getting a bit slow. I think I need to go work out or something. Take a pause from this. Next is to figure out how to run it. I think we've done pretty good on the data set. It should work like this. We just need to figure out how to do the trainer part. I mean, Huggingface is doing it, so we should be able to do it as well. And that will hopefully lead us to a working way of training Whisper with this, and then we can build a cool project using it. But my brain is getting a bit slow, so time for a break. But we got pretty far, at least. I mean, we this is pretty difficult stuff, I would say. It's definitely not straightforward. I mean, fine-tuning Whisper is hard, but converting all this code to using Lightning, I would say, is like 3 levels above just fine-tuning it. And yeah, I mean, so we've done everything here as they've done it, basically, except that we've, instead of using load data set and stuff, we've actually done our from scratch dataset loading, and then we use Lightning data module. And the next steps are first to make the model work, to be able to run it. So basically implement this sequence to sequence trainer kind of, or find a way to do that with Lightning instead. And yeah, that should be a good start, and then we'll do the compute metrics and all of that stuff. And hopefully it won't be too difficult. We'll see. But that's it for the stream. It was a pretty long stream, and you know, I think we can make some pretty cool project if we do. If we get this to work, then we can do, I think, some pretty cool project with it. So I'm hoping I'll figure it out. But yeah, thanks for joining, and see you on the next stream.